Hi guys, in this particular video we'll be discussing the problem of the day for Geeks for Geeks. The problem's name is count even length and the question states that given a number n, find count of all the binary sequences of length 2n such that the sum of the first n bits is same as the sum of the last n bits, and since the number may be very large, so we have to return the answer modulo 10 to the power 9 plus 7. Other constraints have been given to us as n can be up to 10 to the power 5. The expected time complexity for the solution is n log n, and the expected space complexity is order of 1. So with these things in the mind, let's get started. So what the question is asking is that we have to calculate the number of strings that have a length 2n such that the sum of the first n bits and sum of the last n bits is equal. Now a very trivial solution would be to generate all the possible strings and then check for the valid strings, right? The problem with that is that the number of strings of length n, let's say, is 2 to the power n. Over here the length is 2n, so it becomes 2 to the power 2n. Also n is less than or equal to 10 to the power 5, so finally we have 2 to the power 2 into 10 to the power 5 strings. That is a significantly large number and definitely is going to give a TLE. So this is not the approach we can follow. Although the answer would have been correct, but there's no way we are going to generate those many strings. So what could be an optimal approach for this? Even a slight observation would tell us that we are specifically talking about binary strings, right? And a special property of binary string is that it can only contain 0 and 1. Now since 0 cannot have any contribution to the sum itself, anything added with 0 is the thing itself, right? So 0 would have 0 contributions, 0 would have no contributions, all the contributions would be coming by 1. So the problem would boil down to finding all the strings of length 2n such that the first half and the second half, so the first n bits and the last n bits, contain exactly the same number of ones, right? So if it has 2 ones in it, it will also have 2 ones in it. If it have 5 ones, it would also have 5 ones. So let's generalize ones as r. So r would mean the number of ones we are having. Since the length is n, so let's say n is over here. So to give example, let's say n is equal to 3, r is equal to 2. So we are trying to find strings of length 3 which have 2 ones in it. So those strings are 0 1 1, 1 0 1, 1 1 0, right? So these are the 3 strings which have 2 ones in it and are of length 3. So we can populate the first half by any of these 3 strings. We can populate the second half with any of these 3 strings, right? So the total number of strings or valid strings would be 3 into 3. Also, when we try to find this particular thing, so this is called NCR or combinations. So if you are not sure what NCR means, I would highly suggest you to go through combinatorics once and at least read combinations and permutations in detail. These are two topics that are extensively covered in problem solving, and these are definitely going to help you a lot. Over here I won't be going regarding the entire proof regarding this or their applications, but only the required information for this particular question. So NCR is n factorial by n minus r factorial into r factorial. N factorial basically means n into n minus 1 into n minus 2 up to so on to 1. So this is the equation we are having, and since we have to multiply, since we had to square it, over here we have NCR as 3, so we had to multiply it with 3, so we are basically squaring it, right? So it would become NCR into NCR. Also over here we are summing it for r is equal to 0 to n, because over here we were saying that it has r ones in it, so it could have anywhere from 0 to n ones in it. A string could have 0 ones in it, it could be all zeros, or it could have n ones in it, it could be all ones, right? Or it could have 1 ones in it, or it could have 2 ones in it, anything, right? But the upper and the lower limit is are these. So this would be the final solution that we require, or let's say it to be NCR squared. But we cannot directly use this. The problem with this is that since, as explained over here, this is the formula, right? And a factorial means multiplying it, like multiplying that particular number with its descendant, where every other number is just one subtracting by the initial number, right? So this would take order of n complexity. And since we have to perform this particular operation, so calculating NCR is itself taking order of n, right? And we have to calculate NCR n times. So the overall time complexity would become order of n square, which is greater than the expected time complexity of order of n log n. So another approach could be that we could save the factorials. So these are the factorials we are using over here, n factorial minus r factorial, factorial. If we are able to save it in some sort of data structure, let's say hash map, so what we can do is that we can have a lookup in order of one time and then use it. The problem with this particular approach is that using a hash map would incur a space complexity of order of n, which is greater than the expected space complexity of order of 1. So this is definitely not something we can use over here. So what are our remaining options? One option is that if we are able to calculate NCR, if we know NCR minus 1, then we can solve it. Because if you pay attention, then we are calculating all the NCRs from 0 to n. So if we know NC0 and we are able to calculate NC1 from it, we are able to calculate NC2 in it in order of one time. If this derivation is possible in order of one time, then we'll be able to develop a solution, right? Okay, so now for this, let's try to derive this particular formula. Although this particular formula is pretty well known, but just for understanding, let's derive it over here. So NCR is n factorial by n minus r factorial into r factorial. NCR minus 1 is n factorial by n minus r plus 1 factorial into r minus 1 factorial. Let's expand this term a bit. So this becomes n minus r factorial into r minus 1 factorial. So let's expand the terms a bit. So this particular term would now become n minus r plus 1 into n minus r factorial into r minus 1 factorial. Now let's divide the term 1 and term 2. We can divide it and we can cancel out a lot of terms. So these all terms are common. So let's just cancel them out. If we are cancelling these out, so what we'll get is NCR divided by NCR minus 1 is equal to n minus r plus 1 divided by r, or NCR is equal to n minus r plus 1 divided by r into NCR minus 1. So in order of one time, using this particular derivation, we can simply calculate NCR if NCR minus 1 is given to us. However, there's still one problem with it. We are dividing it by a term, so we have a denominator, a non-zero or a non-1 denominator, I'll say. So since we are having a denominator and the entire operation we were trying to do was a modular operation, if you read the question properly, so the question stated that the number could be very large and we have to return the answer modulo 10 to the power 9 plus 7, which is a very well known prime number. So this operation would fail. Now the reason for this is also well known and pretty trivial, but still I'll be going through this if you guys don't know it. So let's say we are trying to compute a divided by b modulo p. So this will so a over here is, for example, let's say a is 6, b is somewhere, let's say 2, p could be 5, right? So a divided by b is 3, modulo p, so modulo 5 is basically 3. Now what if we do the modulus operation first and then try division? So if we do that, then it will become a modulo p divided by b, right? A modulo p is 6, modulo 5 is 1, and we divided by b, that is 2. So now it's 1 by 2. These two terms are not same, and hence we can't operate like this. Whenever we are having some modular arithmetics to do, we cannot do the simple division like this, right? So what's the alternative for this? What we can use is something called modulo inverse. So modulo inverse of a mod p is basically a inverse, and a inverse is a term which when multiplied by a modulo p would give us 1. So this is a very basic definition. Now how do we calculate modulo inverse? There are various methods to calculate modulo inverse, but one of the simplest is using the Little Fermat's theorem, and the only condition for that is that the p should be a prime number. Here p is 10 to the power 9 plus 7, which is a prime number itself, so we can go ahead with that. So modulo inverse using the little Fermat's theorem is basically mod inverse, let's say A mod inverse of A mod P is power of A P minus 2. So this is basically multiplying A P minus 2 times. If we multiplied A P minus 2 times, obviously modulo P, then we will be getting the modulo inverse of A, right? Okay, so with that, our equation finally becomes NCR is equal to NCR minus 1 into N minus R plus 1 into modulo inverse of R. And since we had to multiply NCR into NCR for each term, what we can do is that we can start a for loop or any looping for that matter. In each loop, we'll be calculating the NCR using the previous NCR minus 1, and then we'll be adding NCR into our answer, and then we can simply return the answer. So this particular question had a very simple implementation, but there was some theory behind it. I hope I was able to explain you the theory. Now let's get back to the question and let's try submitting it. So over here I have taken P as 10 to the power 9 plus 7. The result I have taken as 1. The only reason for that is that I have started the loop from 1 itself, and this and since NC naught also needs to be considered, so I have already added 1 to the solution. So NC naught is always 1, so I have added this, right? Also NCR is 1, so initially NCR means NC naught, and this is 1. So in the first iteration, that is for r is equal to 1, we will be calculating NC1, and NC1 would be equal to n minus r plus 1 into NCR. So over here this NCR is 0, so n minus r plus 1 into NC naught into modulo inverse of r as discussed in the solution, and then we will be adding this particular value squared to a result variable. So the only reason I have mentioned this one LL over here, you can see, is to avoid overflows. So what happens is that when you perform any sort of multiplication, so there's a possibility that it overflows. Let's say our NCR was somewhere around, let's say 1 with 6 zeros, so basically 10 to the power 6. Let's say it was 10 to the power 6. Now as soon as I perform NCR into NCR, right, so it would become 10 to the power 12. However, the capacity of an int is to store only 10 to the power 9, or let's say 2 into 10 to the power 9, right? Since this number is very smaller, or it's smaller than this particular number, hence it would overflow, right? And as soon as it overflows, it would give you an incorrect value, probably and most probably a negative value. We want to avoid that. Hence what we do is that we mention a 1LL before that. So what happens is that when this particular value is getting computed, so it tells that it is a long variable, right? So it's a constant, but it's of the type long. So when it will get multiplied, so the result would be in long, and then like the long has a time has a capacity of holding 10 to the power 16, right? So it won't overflow, or 10 to the power 18, I guess. So it has a capacity of 10 to the power 18, hence it won't overflow. Okay, so I think that was enough of an explanation. You must have got the concept, and the algorithm is also very simple if you want to check modulo inverse. So this is how I've calculated modulo inverse. So using the little Fermat's theorem, right? So it's basically power x comma p minus 2, because our p was a prime number over here. The way I've calculated power is also simple. So let's try to submit this particular code. Okay, so this takes just 0.28 seconds to compute, and all the test cases are passed as well. So our algorithm is correct. I hope you were able to understand all the concepts that were involved in this particular question. If there are any doubts, you can let me know. Thanks guys.